We're here. We are loud. I apologize in advance. No, I apologize retrospectively to your eardrums. I I had turned off the ATEM, turned it back on, forgot to change the level. Hopefully it's okay now. So the first screw up is before I even began. That's one out of the way. I acknowledge the traditional owners of this land, the Whadjuk Noongar peoples. I pay my respects to their elders, past and present, and to Aboriginal elders and peoples from other communities who may be taking part in this live stream today. I hear that we need to send Brussels sprouts to Pete. Speak up. Speak up. Why? Did I deafen you? Hey, so, good morning, Pete. Railway tap. Railway tap? Good morning too. Crispian, Railway tap. Simon CBR, Imi, John Whips, Sharky, Grant Mazels, Stephen 447. I clicked it and I didn't see the rest of the numbers, sorry. If that's your surname. That's your family name, 44799. Dennis Trees. Oh, cool. Haven't seen you in the chat for a little while. It's cool to see you. Who else is here? Stephen says if you look really hard, I'm sure you can find a box to play in somewhere in Bayswater. I wouldn't even have to look outside this room. There are plenty of boxes for me to play in. Yeah, I can be a cat. I can play in a box. I can order something, take it out, and play in the box. Now, today, I'm pretty sure that Vic is not here right now because he was having a day, how does he put it? Turning dollars into noise? Something like that. He was having a day out on the shooting range, and but it's expected to be very, very wet where he's in New Zealand right now today, and didn't think that he would be out there for very long. But even in his absence, I feel the need to apologise to Vic because, what is it now? It's May. It's 10th of May. So much time has gone by. I've been meandering along on this project and just sort of treating it as a thing that I will do little bits of, and I do like a 2.5 hour live stream and put 2 nuts into a 3D printed piece, and that's the entire stream. I am not making good forward progress on this project. So, Vic is here. Vic says, just got in. Also, hello to SK Photo Guy, Paul Schultz, and Vic, the man himself, Oliver. So, I apologize, Vic. I did say, like way back in January at Everything Open, when I was saying I'd like to build one of these, I did say that I am very slow. It'll probably take me ages. I will stuff around. But yeah, I still feel really bad about it. So today we are going to make a little bit more progress, possibly move slightly sideways, get the steppers spinning. In fact, I think that is probably a good thing to experiment with right up front. So I am going to show you, I'm going to switch cameras, and I'm going to show you what I am up to. But I need to make sure I've got the chat. Oh, excuse me. I've got to make sure I've got the chat visible. Where is the chat? I can't even see it right now. There's a window here somewhere. It's got to be there. It's got to be there. Oh, there it is. It was covered by cast note. Here we go. Okay. So, oh, hang on. I've got to mute myself for a second. Okay, just had to clear the throat. It still feels like it's not clear. So let's go to this. Now, something that you have seen previously is this. Sideways. Yeah, Crispian does like going sideways. bit of oversteer, brake traction on the back, and then steer into it, keep the back wheel spinning. Okay, so this is the Pika, and you can see the platform there moving. It's got the nuts in it, it's got the bolts in it that are holding the nuts and keeping them from falling out, although they're not exactly going to fall out anyway, they're pretty tight. We've got nuts in place in all these various slots for attaching other pieces, like the axis drivers. There is the bottom piece that is attached. Because I'm holding this up close to the camera, it's slightly out of focus. The camera is focused down more in this area. I'll put the Pika aside for now. Oh, I also have two different generations of the stage mechanism. I'll put those back over there. I've got a whole bag of loom bands, which we are possibly going to need in a minute for backlash compensation on here. I have 3 of these driver assemblies with the NEMA 17s and 50mm M3s, which are full thread. I've drawn little lines on these. If you look straight down, you'll see that there are 3 lines on each of these little couplings. That is so that when it turns, you can see it on camera, because hopefully we're going to be powering these up today, making them move. So I've got 3 of those assembled in the 3 different colors, so different color for each axis. These are the nuts that are drilled out, so they are going to be the bearings that go onto these threaded rods. I've got all the parts here for each of the 3 axis drivers. The axis drivers have all of their nuts in place. Oh, Pete! Thank you, Pete. Is that for my Brussels sprout fund? My goal in life is the acquisition of turnips. So, yeah, so we've got the nuts in place on all of these, ready for attaching the things that need to go onto them. And where else are we? Oh, I just realized there are nut mount. I don't think I've got nuts into the insides of these. All right, we shall see what happens when we get to that point. So I've got these 3 that are all in that same shape. They've got all of the nuts in them. So we've got a whole lot of the building blocks here. We've got many of the subsystems in place. One of the next steps to do is to finish...
Waltep said, how about Steve's nuts?
How about Steve's nuts? Steve the squirrel has hidden his nuts. They are where you will not find them.
Going nuts again.
Yep. Okay, so Vic says those extra nut holes are only used in the Z-axis driver. Cool, no problem. So that's on the inside here. There's I mean, you can't really see where I'm pointing to. If I use a pair of angled tweezers, you can see these 2 holes on the side. On the back side of those holes, right in here, where I cannot get the camera angle to show it, there is a little hexagonal recess so that nuts can go into there, so that screws can go in from this side and then grip onto those nuts. So that is for only the Z-axis driver, as Vic just clarified for me. So that is pretty much all the 3D printed parts, I believe. I think everything is printed. What I need to do is... oh, my chest is not going to cooperate today. So what I need to do is finish with the attachment of the actual steppers and these parts. So this is part of the guide. You can see there's a spot there where a nut goes in. That's where one of the drilled out nuts goes, these drilled out nuts. So that is a guide for the M3. And this is a spacer that can go in the middle to increase the tension if the bands that go around it for the backlash compensation are not applying enough force. What else do we have?
The long slots
Mounts.
aren't used in Piker.
The long slots aren't used? Okay, so the long slots aren't used. So that's these ones, I guess. These could be leftovers from a previous print, because I've printed several generations of the hardware now. So Vic, just to confirm, yeah, okay, cool. So these ones, let's get rid of those. I will take those out of the mix, throw them aside. Speaking of which, something I've become much more conscious of recently is, because I'm printing so much, I've been throwing out a lot of plastic, and I don't like it. So one thing that has been in my in my mind for a little while is some kind of a filament extrusion machine. I want to be able to throw a big tub of pieces, like if I grab a whole lot of printed parts like this that I don't need anymore, throw them into a hopper, have them ground up, turned into a filament that is just like a mix. Obviously it's going to be the mix of whatever the colors are. So that'd be really useful to have a reasonable supply of a filament that is not a specific color. It's just use it to print test pieces or whatever, because I have a lot of fairly large 3D printed things, including multiple peakers.
Tinker001 said 3D unprinter.
Yes, 3D unprinter. And yeah, so anyway, I don't want to get too much sidetracked by that, but that is something that if anyone has actual hands-on experience with it, because I've seen many people talking about that sort of thing, if any of you have actually created your own filament by grinding, melting, extruding, using any of the available tools or open source solutions that are out there at the moment, I would love to hear about it. So in this case specifically PLA. I don't know how whether PLA is a good candidate for reprocessing back into filament or not. But anyway, that's something that I have been conscious of recently that I want to look into. Because in the past what I've done is thrown all of my failed prints, just thrown them in the bin, and a fair bit of it goes out into rubbish disposal. And just recently I started accumulating it, so I got a plastic tub, and whenever I have a failed print or all of the poop that comes out of the bamboo when it does its filament change, I throw it in that tub. So I've got a tub of 3D printed stuff, enough to make quite a lot of filament already. So got all of that 3D printed stuff there. Then what I have, let's see, how can I move these far enough out of the way? I think I can to make, yep, to make some space. I'll move that. I'm going to return to those 3D printed mechanisms because there is something else I need to do before we do that, which is I need to connect these up to this. This is what I'm going to try using as the motion controller. It's not the same as what Vic is using, but hopefully it'll do the job. This is a Tiny G motion controller, and I've got a couple of these. There is one running Mickle Make It, so my DIY pick and place machine runs on one of these, and it seems to it seems to do a pretty good job. It's got, I mean, not that it matters so much for this project, but one of the nice things about this is that it has third order motion control. So it does S-curve acceleration. Oh, what is, I wasn't really coughing like this until the stream. It doesn't feel like there's anything in my throat. It's just this urge to cough. It's annoying. So it's got 4 stepper motor drivers here and G-code interface. It's got a whole lot of configuration options. It's got various I/O that can be used for things like limit switches, spindle control. The labels on here, if I can read them, ground, spindle, ester. So what you can do is have a PWM control of a spindle if you're using this for running a CNC machine. Cool. Yeah, PWM, there's a cool output, so that's for running coolant into a CNC machine. And Xmin, Xmax, Y min, Y max, Z min, Z max, A. So A is typically used for like a rotational axis, and 3.3 volts. So it's got max min limit switch inputs for all 4 axes, and they are, yeah, they're generally just a pretty solid little motion control board which accept G-code. So we should be able to use this to drive the, Vic says PLA does not recycle as filament well. It starts degrading during processing. Trust me. Okay, that's interesting to know. PETG recycles much better. Yeah. Okay. Right. Now, what I want to do is connect up to this motion controller because it's in a bit of an unknown state. This has been sitting in a box for years since I started this up. I don't even know, I'm not sure what the connections are on the coils on these. I assume that these are standard sort of things, so it's going to be red-blue for one coil and black-green for the other, which seems to be the convention on these steppers. So the first thing is I want to connect the steppers to this and log in on its console, and we'll see what the settings are and see if we can make the steppers spin. And that at least will let us get started with then finishing the assembly of putting these axis drivers together with limit switches. And I think what I want to do is test that before it actually gets attached to these axis drivers. Because if I attach the motor and screw it up, like if for example, I have my software settings wrong, or if I have the limit switch not being read properly and it overshoots its position, it could damage this mechanism. So I want to make sure that the steppers are being driven in a controlled way before they can actually damage anything. So just while they are sitting here spinning in the air. So that is my first step. I'm going to hook these up and see, what am I going to do? Okay, I'm going to undo that knot. So I'm going to hook these up and then we'll jump on the console for this and see what we can find in the settings. So in the meantime, if anybody feels like looking up tiny G documentation or tiny G settings, feel free, because that is what I'm going to be doing once I get to the point of trying to drive it, because it's so long. And it's years since I've messed around with driving G-code manually.
First step, test stepping. Makes sense.
Yep, cool. Who said that? Tinker, yes. Yes, I just want to test the stepping steps. So, Vic says, for those who don't know, guess who invented PLA filament? Try finding that on Google. I think it was you, wasn't it, Vic? Was it you or Adrian? Who was it that invented PLA filament? Come on, don't be shy. You can answer the question. So, motor 1, it's numbered from right to left. And I don't know why, that's just the way it is. I'm going to get this out of the way, get all these cables out of the way. And I'll do it here so that we can see it. Now, what order do I want? So it's going A1, A2, B1, B2. And so I'll go red, blue as the first coil. Red, blue. And then green, black as the second coil. So coil A, coil B. And then we'll see. Also, I don't know what the current limits are set to or anything like that. On this motion controller. See these trim pots here, which are all currently pointing straight up to 12 o'clock. They are the current limit setting. And if you have, so the way steppers work, you can tell your controller to do position hold, or it can move the stepper and then let it go. And if you have position hold, so keep the motor energized, it keeps running current through the motor continuously, even when it's not moving. Because what it's doing is keeping, there are the different coils of the stepper, which have current running through them, and depending on the combination of coils, it holds the magnets in a certain position. And so if you turn the stepper off, there is no more magnetic field to hold the magnets or to try to make them move, so it just spins like this. I can just turn this by my hand, no problem. But if you keep the coils powered up in the configuration of the position that you want it to have moved to, it then resists movement, so it locks in place. And the more current you run through the coils, the stronger it locks in place. So, but also, as you can imagine, if you're running power through the coils, they get warm because that energy has to go somewhere. So, yeah, you just have to make that decision in the design as to whether you want position hold, in which case you're going to have current flowing continuously and the motors are going to heat up, or do you let them just sit? Now, for this application, of course, we're going to want motor hold, because we do not want those motors to move influenced by any external force. Although, because it's going through you could probably get away without it, but still, I think for the sake of keeping a very consistent position, we are going to want to lock those motors in place. Vic says, yes, me. Haha, yes. So, yeah, PLA filament was invented by Vic. Okay, move that out of the way. Ah! Here I am dropping stuff. That one. Grab this one. Okay, last motor. I could have just started it with one motor to test, but no. I want to try them all. So what we're going to have to do also is figure out some calibration on this, because when you are doing when you send a command to a stepper motor to move a certain number of steps, how far it moves is going to depend on the resolution of the motor and the mechanical structure of what you're driving. So like in this case, it's the pitch of the M3 threaded rod or the bolt, and any like mechanical advantage that's in place, levers, all that sort of thing. So or if you're driving something like a belt drive, then it comes down to things like the diameter of the wheel that you have driving the belt. All these factors that you have to allow for. Now, if I got this right, red, blue, green, black, red, blue, green, black, red, blue, green, black. Looks okay. Okay, and now we have 3 motors. Looking almost straight up at the camera. So, I'm going to do, I'm going to apply power.
Chica001 said, gonna be real interesting when he fires it up, the steppers start running in 3 different directions.
Yeah. Yeah, because I've got no idea what the settings are on this Tiny G. All right, I'm going to plug that in. I'm going to turn on power to the Tiny G. Okay, it's alive. Now, it shouldn't do anything by default. Oh, it looks like it's just finished booting. It shouldn't actually make it move at all. The motors I can move, so it does not have the setting to keep them energized, it would seem. I think, from memory, the way I had this set up on Mick or Make It was, it would keep them energized for a certain number of seconds after a movement. So it would move.
Chica001 said, actual joke missed.
Actual joke missed? Oh, okay. Yeah, it went right over my head. So the way I had it set was that if you sent a command to move a stepper, it would spin the stepper to the target number of steps or position or whatever, and then it would hold it energized for a certain period of time. I think it might have been 30 seconds or some period like that, and then it would release the stepper. And that would allow...
Using 256 step, you'll need 32 steps per micron or so.
Yeah, this one is... yeah, okay. Cool, we will get to that in a second. So Vic said, if using 256 steps, you will need 32 steps per micron. Okay, so I don't actually know what the resolution is on this. So part of this is I'm going to have to look up. This may not end up being a suitable motor driver, but hopefully it'll be enough to figure things out.
Or half that for your 200 steps per revolution motion.
Yeah, these ones are 400 step per revolution steppers. They are 0.9 degree steppers. So let's, what are we going to do? Okay, first thing is, I'll leave that in view while I grab a tissue and let's have a look at what we can find for a tiny g. Tiny g. Tiny g. Tiny g motion controller board V8. Oh, there's a link to Adafruit. Yeah, there it is. Out of stock. Yeah, these things are really old. They haven't been sold for a very long time. Yeah, they were intended, I believe. Micro stepping up to 1/8. Makes this smoother than 1/16. Okay, so you're talking about 256th step. Okay, I think I may need a better motion controller. Tiny G Wiki, but this is what I've got right now, so let's see. Oh yeah, look, the wiki was last updated 2019. It is very old. What is Tiny G? Tiny G start page. Okay, so configuring, connecting, configuring. We've got all of this. Fan, we don't care about. Current. Okay, so between 8 p.m. and 4 p.m. position only. Between 8 p.m. and 4 position only. Right, so that is, yeah, 8, that, yeah, okay. That's a strange way of putting it. John! G'day, John. Fan, we don't have anything connected. Power, most people use 24, 19 or 12 volt power supplies. Yeah, I've just got 12 volts plugged into it right now. Yeah, Paul says, Adafruit shows Tiny G is out of stock. Yeah, it's been out of, it hasn't actually been in production for like 5 years. So, you can't, I'm pretty sure you haven't been able to buy them for years and years. Oh, okay. Vic says, 256 divided by 32 equals 1, so close enough. Cool. All right. Start with the current setting trim pots in the middle, 6 o'clock straight up down position. Yes, so that is where everything is. I don't need to do an update. Steppers, power supply is plugged in. It's plugged into my lab power supply with a current limit set to 4 amps, 12 volts, 4 amps. Should be fine to get started. Cooling. Program the debugger. Okay, let us connect. Cool term. No, I do not want to go to a new version of Cool Term. Let's see if the serial port has come up. There it is, USB serial. What is the baud rate? I can't remember. I think it might be 115200. Terminal I'm going to put into line mode because I want to be able to formulate things. Oh, there's something going on there. Let's see what happens. Help. Woohoo! Look at that. We're talking to a Tiny G. Tiny G configuration help. Can I do a factory reset. So this is one of those things where it's been, how long has it been? Probably 5 years since I have messed around with TinyG config, and I cannot remember. Sys. Okay, so system general settings, show all settings, so I can do sys. So we've got firmware build 440.2.97, hardware version 8. Yeah, junction acceleration, chordal tolerance, status interval 250 milliseconds, that'll do. So it's going to send us an update 4 times a second. We've got text mode on, we're not running JSON mode. Oh yeah, we've got a 2-second motor idle timeout. This is what I was talking about. So it's set to 2 seconds, not 30 seconds. And you can also set, so I'm pretty sure the way this works in the TinyG is there are global config options which are then overridden on a per axis basis. So we can have things like motor idle timeout set to 2 seconds, and then you could override that for one of the motor outputs and set it to something different. But it defaults to whatever is set here in the global settings. Network mode, master, US baud rate 5, yeah, 115.200. Expand line feeds, no, don't care about that. Default G-code chord system, yeah, okay. It would be interesting to see if we can do a factory reset on this. But what I should do, nope, I can't do that. Can I make the font bigger? Serial port, data handling, miscellaneous. Where is, oh, maybe it's under the view menu. View. Please, nope. Settings. SQL date time gone. Scripting, updates. Nope. Where do I change the font settings? I want to make it bigger. I don't know. Oh, view? No, that's just the view mode. Oh well, looks like we can't change the font settings in CoolTemp. Okay, what do we have here? X offset, Y offset 75 millimeters. Yeah, there are probably settings in here that were relevant to the homing system that I was using on the pick and place machine. Where I had things like, I'd have it home and then back off from the home position. So there'll be A search velocity, B maximum velocity, all of these sorts of things are probably going to need tuning. Jerk settings, jerk homing. So the jerk setting here, jerk settings are in relation to the third order optimization on the motion curve. So that's to eliminate any jerk as it's moving. TinyG jerk control. I want to see if there was a, let's see this. TinyG, let's see if I can do this. I'm going to mute it. Oh yeah, this is impressive. So this was testing of the TinyG. So you can see that there's no jerk control and it's just moving quickly to its target. And then if we come along here somewhere, so like this, yep. Somewhere here, yeah, this is where it's got third order control turned on, I think. So watch the liquid in here. It's really impressive. It's not just an acceleration curve. It's like it's doing some clever calculations to figure out the. So this is that I think is, where does it say what it is? I think this is second order. Can it both jerk and feed rate, and then the third, yeah, wherever it is. Anyway, the point is that it can do incredibly smooth motion. There's another one that I saw where it was running a pendulum. This is years and years ago though. I'm trying to remember what I saw. Tony G, motion control, pendulum? Yeah, it was like a balance thingy tutorial. Just trying to find where this was. I know that's a presentation about it. I'm just looking through other videos off screen so that I can check. Oh, maybe here. There is some kind of control demo going on here where I think they were running, yeah, that's right. So this is an XY platform, oh, XYZ, and it's got a pendulum hanging from it. And look how stable it is after it's finished its movement. I mean, this is not a great demo, but the idea is that if you have a mass that is hanging from the XY platform and you just do a direct move and then stop, what will happen is that it'll end up just swinging like this. But if you do third order motion control, you can basically have it so that it swings and it will stop at the end of its swing. And so you can take a hanging weight and move it, you can translate it through space and have it stop at a certain location and not have any residual swing. It'll just move to that point and stop. It's, when you see it done properly and well tuned, it looks amazing. Really, really cool. Yeah. Ooh. What's going? Oh, Vic has just sent a link. What's this link? What's this link? Continue. Let's see. Superhouse live stream supplemental. Ooh, nice. Vic has just sent this through. 10 to me. Gerbil step setup is as follows. Okay, so this is using Gerbil, which is homing locate feed rate, millimeters a second. Yeah, which is very similar in some ways. Like many of the configurations will be the same. Things like homing locate feed rate in millimeters a minute. That sort of thing I can directly take into the settings in here in Tiny G. Awesome. Thanks, Vic. Okay, so let's see if I can find Tiny G. Is there a factory reset? Julie Papa, power management, discussion topics, milling, noisy spindles, etc. No. Is there? Where are the? Somewhere here. I'm pretty sure there is a factory reset setting. Factory. Reset to factory defaults. Here we go. Let's do this. Defa. 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 What did that do? Oh, it says okay. Restore to system defaults. Defa equals 1. Okay, so we want defa equals 1. and resetting to defaults. Now, I've got to remind myself, does this save to flash? I have a feeling that what happens is you can change settings in memory, but it doesn't write to flash. Although the factory reset may have done that. What is the write to flash? Flash. Flashing? No, I don't want flashing. I want write to flash. What about save? Save. Nope. Okay. I had a vague recollection that I've got to manually tell it to save the changes to the settings, but maybe not. All right, so what do we have here? If we just do $, we get a dump of all of the settings. So let's have a look at the settings that Vic has just sent through. So we've got this lot of settings, and we want to apply in here. So what can we extract from here? Step pulse time microseconds. This sort of thing is going to be specific to the controller and the stepper motors. Step idle delay, step pulse invert. Okay. Oh, Paul says, just fired up the Melzi Dentissimo board from Huxley, getting serial messages. Woohoo, SD init fail, all good as there is no SD card installed. Uses an 18 mega 64p. What are you using that for, Paul? So you got a, oh, you'd be using that for a RepRapMicron as well. Ah, Melzi Ardentissimo board. Okay. So for those of you who aren't aware, Paul is also building a RepRapMicron. Tinker, extra thick crepes. Oh, hang on, I had muted my computer earlier.
Extra thick crepes.
Yeah. Crispian says, got to replace breakfast with yummy eats while we watch Uncle John. Okay, so step pulse invert. Okay, so there might be some direction things I need to figure out. I'm pretty sure that in the what's it called again? The tiny g. Things like directions of each of the axes. So these are the M1. So that's motor 1. Okay, M1 step angle is set to 1.8 degrees because that's default. I've got to change that. And also you can, yeah, this is step angle polarity, normal reverse. You can see here we've got step pulse invert mask. So $2 equals 4 in the gerbil
Big
config.
gotcha is that Z homes towards the maximum sensor.
Okay. So Z homes towards the maximum sensor. Oh, Paul says, how are you sending commands to serial? I'm using CoolTerm. This is just a serial console program running on Mac, and I've turned on, if I go into options, terminal, I've turned on line mode so that I can type a command into an input box and then press enter to send it all as one thing instead of having it in raw mode where every time I type a character it sends it. Raw mode works fine, it's just that if you make a typo you can't delete and then fix it before you send it. So I just open the serial port, before you open it you got to set it all up. So I set it into line mode, set the serial port as the target device, set the speed, and open the connection. So I just click connect. Yeah, so the way Gerbil works with its config is that it uses, it's very memory constrained, really, really memory constrained. So what it does is it compresses a whole lot of the config options into things like bit masks and doesn't unwrap that at the user interface level by user interface, I mean the serial console. So things like step pulse invert, which is a mask, the config value 2 here is set to a value of 4, which then sets certain bits within that byte, and each bit represents an inversion flag for a specific axis. And so by giving it a different value there, you can set different bits and you can invert different axes. So that's done like in a single value on Gerbil. In the TinyG, internally it may well save it as a single byte with flags, like bit flags for specific axes. But in terms of the way you configure it, it breaks it out into separate config variable values. So you can see, where was I? Yeah, you can see things like axis mode, direction, those sorts of things as being individual values that you set. Where are we? Step direction invert. Step pulse invert, step direction invert. Sorry, step direction invert is I was saying the wrong value. The direction invert is set to 3 here. Wagon loads. Okay, so Tinker is here. Also Amanda, Gavin Jackson, David Crisp. Yes, and wagon loads. Welcome. Reports in inches. No. Soft limits enable, no, set to no. Hard limits enable, yes. Homing cycle enable, yes. Homing direction invert mask. Okay, so this is what I think Vic was just talking about, where the Z-axis will be homing in the opposite direction. So that's an inversion on the Z-axis. So we've got homing locate feed rate in millimeters a minute. Now what I should do is change, I mean, none of this really matters in terms of just making the motors spin, but I'm going to change the, okay, let's just have a look at the motor 1 config. Is that it? No, or is it 1? Oh, it's 1. Okay. 1. Yeah. No. I thought that was how I could do things in 1M. No. I thought I could do masks, but I couldn't. Or can I? Yes, I can. Yes, I can. Okay. So if I do $1, it shows me. So this is one thing that is nice about TinyG. 1M, yeah, I just did $1. If you do $, it shows you all of the config options. There are hundreds of them. But you can filter it down and just have it show you specific ones. So if I want to deal with axis 1 only, I do $1. And then it shows me the config related to 1 blah. So I could do, so map to axis. First one is x-axis. And by default, basically, it'll do motor 1 to x, motor 2 to y, motor 3 to z. Step angle is set to 1.8 degrees, which is wrong. M1 travel per revolution is currently set to 1.25 millimeters, which is almost certainly wrong. Microsteps is set to 8, which is okay. That's the maximum setting on here. Polarity is either normal or reverse. And power management, 2, is in cycle. Okay, so this is where we tell it whether to hold power to the motor or not. 0 means disabled. So, 0 is disabled, which means it does not keep the motor energized unless it's moving. If it's 2, it keeps it energized always. So whether it's moving or not, it always sends power through the motor to hold its position. 2 is in cycle, and I'm going to come back to that. So 3, when moving, is it powers it, moves it, and then disables it. So which it seems a little bit counterintuitive. Sorry, 0 disabled is it won't ever power the motor. So you can tell the motor to move and it will not move. There is no power to it. Effectively, the motor is disabled. 3 is it is powered when it's moving, and then as soon as the motor stops moving, it removes power. 2, which is the default value, is in cycle. And my memory of that is that what it means is that if, for example, you send a compound command like G0X50Y100, which is telling it to move to 50 in the x-axis and 100 in the y-axis, it's going to move 2 motors at the same time. One motor is probably going to move for a longer period of time than the other, or it depends on whether you're doing like direct path and it slows down one motor, or if it's going to go at 45 degrees and then straight, like if it runs both motors at full speed. So there are all those complications. But in cycle basically means that a motor is moving. And so if you want to stop vibration from making your device move, say you're moving or just moving the x-axis, while you're moving the x-axis, you also want to energize the y motor so that it locks it in place. So as you're moving in x, you don't get just vibration making the y move out of position, and now you've lost your accuracy. So in cycle is the default. You can see here, M1 power management is set to 2. So in cycle means energize the motors, hold them in position when any motor is moving. So that way, if the machine is bumped, you're not going to lose position. When moving means that it'll only energize the motor while it's moving. If you've got another motor moving, it won't energize this one. So you're more liable to have errors in your position. So in cycle or always on are probably what we want. Okay. So, have a while back of the infinitely prolonged what? From
Have you had your visit from Wowbagger the infinitely prolonged?
That must be, that's a reference to something. I don't remember where that reference is from, sorry. Is that a Douglas Adams reference? Or is it a Terry Pratchett reference? It feels like one of those. Okay, so you need a position. Crispian says, yep. Wagon Load said, DA, yeah, Douglas Adams. Wagon Load says you need a position feedback loop. Yeah, so that's the difference between open loop and closed loop control. These are steppers, they are not servos. They do not have feedback on their current position. So we are just doing our best. We're blindly sending commands to make them move and then hoping that they do what we want. So let's just check a couple of other things. What have we got on here? Oh, that's right. What I was going to do was change. So we can change $1 SA, which is step angle, equals 0.9. Let's see if this works. 0.9 degrees. Nice. So now I'm going to change motor 2 step angle, motor 3 step angle. They are now set to 0.9 degrees each because they are 400 step per revolution steppers. So if we do $1 to show motor 1 settings, it is now set to 0.9 degrees. M1 steps per revolution I need to figure out, but this should be enough to, where are we? X-axis travel resolution steps per millimeter. Y-axis steps per millimeter, Z steps per
Stepper
millimeter.
control is much like instructing your children over the phone.
Over the phone, yeah. Wagonload says, can you put rotary encoders on the motor shafts? Oh, I could just go to closed loop, stepper servo type things. Yeah, that would be the more advanced way to do it, but I don't have those. Something like a let's see what I can find. Oh yeah, the MKS, this sort of thing. RS485, CAN board. Yeah, this sort of thing. So a stepper motor, so it's an EMA 17 stepper, closed loop, with position encoding on it. So yeah, you can get this one with a CAN bus interface or with RS485. So yes, we could do something like that. We could put one of these on it, or 3 of these on it, but we'd need to get ones that are 0.9 degree and CAN board. Yeah, and then we would need a controller that sends CAN bus messages to them and reads CAN bus data coming back to get the close. Oh, it could be RS485, but I prefer to use CAN bus. It's just what I'm more familiar with. Yeah. So yes, you certainly could do that if you wanted to make it a closed loop system, but most 3D printers just use open loop, and they home, and then they just don't miss steps, you hope. So that should be okay. For now, I am going to proceed with this. So we've got I think these 3 are going to be, these sorts of things are going to be important. This is where the tuning is going to come in to set the calibration. So y-axis maximum rate, millimeters a minute, 15,000 millimeters a minute. Millimeter. Okay, so what have we got here? Travel per revolution, microsteps, polarity, power management. And then I think there are a whole lot of settings per axis. So let's just do $X and see what settings we've got. Okay, we have these settings for the X-axis. So the way the TinyG works, it has motor drivers and it has axes, and you map motor drivers to axes. So you can, in this case, for example, if we look at motor 1, we can see motor 1 has been mapped to axis 0, which is X. So you can do fancy things like bind multiple motors to an axis, or yeah, so you can do things like drive one motor forwards and one motor backwards on the same axis if you've got opposing facing steppers on the Y gantry of a machine, on a machine, for example. Lots of fancy stuff you can do with TinyG. So we've got motor 1 mapped to axis 0, which is the X-axis, and then we have the X-axis setting. So standard means that it is a linear motion axis. You can have linear motion axes and you can have rotational axes. So we've got X velocity maximum, feed rate maximum, travel minimum, travel maximum. So it's 150 millimeter range of travel. It can go from 0 to 150. And then we've got jerk settings, which is the 3rd order stuff. We've got limit switch settings, search velocity, latch velocity, and back off. So once it hits the limit switch, it then backs off again by a certain distance. Latch velocity, search velocity. So yeah, for now, I just want to make these motors spin, so I don't really care that much about any of these things. I just want to be able to send it a command and see what happens. So what we could do is, I'm going to do G0 X, I don't know, 100, just to see the world burn. Okay, I actually have no idea if this is gonna work. I'm gonna switch to the overhead camera. If this works, I am going to be kind of shocked. Okay, switch to the overhead camera. One of these, where are we? Motor 1, which is this one. It's the yellow one, okay, which luckily is quite easy to see. Now, I'm gonna hit enter in a second, and we'll see if motor 1 turns. I bet it will do absolutely nothing. Whoa, it spun. And, what? That was weird. That was very weird. You could see that it started and then stopped.
About 16 revolutions before the top unscrews.
Okay, I'm going to go back to, I'm going to do a G0X0. It may be spinning too fast. What is its boggle? All right, I'm going to try again. Yeah, you can hear it. No, it's not. Oh, I know. The stepper is not responding. It's all right. Okay, there is some tuning to do here. We have some control, but we need to do some tuning. It's trying to run it too fast. Oh, Vic says your steppers are not wired properly. Ah, okay. Stepper's not wired properly. Cool. Let's figure that out. So it starts to spin. I thought that it was just overdriving the rate. I'm going to try... Okay. Looks like too fast and too much Excel, says Simon. Yeah, it should be kind of conservative. I am, just so that we can see things going on, I'm going to change some settings. Vic says, check continuity on A1 and A2. Yep.
Check continuity on A1, A2.
I will do that. But I'm going to pull motor 1 settings and X-axis settings up on the screen. And then I'm going to grab the multimeter and see what's going on. So we've got normal, micro steps is set to 8. Power is in cycle, which is fine. Velocity maximum 800 millimeters a minute. Maximum you got 15,000 millimeters a minute. Yep, so the setting is very slow. I don't think that's going to be the problem. Travel maximum 150 millimeters. It's not trying to run the stepper super fast. So I don't think that's the problem. I think Vic is on the money that there is a problem with the wiring of the stepper. Just as a quick check, let's do G0Y100 and see if we get the same behavior. So the Y will be the green one, and I'm going to hit enter. Yeah, same behavior on that. So let's check the wiring. And let's check the wiring. I'm going to take off, which is it? So red and blue, which is the A connections on that stepper. So these two. What reading do I get across there? I've got my multimeter that sadly you can't see. I've got to fix that. It's reading 4.4 ohms. 4.4 ohms.
Unpulsed power.
Sorry, what was that? I missed that. Unplug power, says Vic. Okay. Unplug power. I will turn off power. There. I've turned off power. I don't think it would have been hitting the current limit because we would have seen other symptoms then. But I was not actually paying any attention to current either. It is possible that it was hitting current limit when it was ramping up to max. I'm just going to do another little test here. I'm going to do G0Y100, and I'm going to watch the lab power supply while I do it. No, it's running, it's pulling about 1.1 amps, but it could be hitting the current limit on here. So, where is it? I'm going to turn the current limit up a little bit and see if that makes any difference. And do this. Aha, look at that. I think it was hitting the current limit. So it is now spinning continuously, and then it should slow down. And then 2 seconds later, power goes off. Yeah, I think it was just hitting the current limit. That's all it was. Vic says, unplugging stepper before power can blow the stepper driver. Ooh, okay. That was dangerous of me then. All right, I'm going to increase the current limit on all 3 of these drivers. So there is tuning you can do to figure out the actual, like there is a whole process around setting the current limit so that it has enough power to run, but not get hot. Okay, now I'm going to change the power mode. I'm going to turn constant power on, so it's going to lock the motors and run current through them. I'm going to see what happens to the lab power supply, which is currently set to 4 amps, and I want to see if the motors get warm. So back over here, what is the, where are we? Oh, here, look at this. In the console, you can see all the position reporting. POSX values coming back. POSX, velocity, and there's a status once it's actually reached its end point, its target position. So we sent a move command, and then we got a bunch of feedback as to what it was doing. So based on the settings before, it is sending a feedback message every 250 milliseconds. So that represents a few seconds worth of movement. Wagon Load says, I saw the yellow disc spin for about a second, then stop while I still heard buzz. Yeah, that is exactly what was going on before. So I'm going to, all right, I'm going to verify this. No, I'm not. Before I do that, I'm going to turn on, where is it? The power management mode. On motor 1, I'm going to set to always on. So 1 p.m, I'm going to set to 1. 1 p.m. equals 1, and now the motor should start powering. Yep, I can hear it. It's like a high-pitched whistle. You probably can't hear it. Or mate, I don't know if it's going to be picked up on the microphone or not. So motor 1, yeah, that is now locked in position. Oh, really hard actually. It's quite strong. Whereas this, I can turn it no problem because the motor is powered down. But this one is doing its position hold thing. It is currently pulling 2 amps that I can see on the lab power supply. And I can just, so far, I can just barely feel it starting to warm up. It'll take a little while. They take a while for temperature to stabilize. This one feels cold. This one feels warm. So I'm going to leave that one sitting there. But what I might do, funny thing is that the way steppers work, when they're in position hold, they pull more current than when they're moving. So the worst case scenario for it is sitting here stationary in position hold. So it's currently pulling 2.2 amps and slowly rising as the stepper warms up. The current consumption increases.
You can turn the amps down a bit.
Yeah, I could turn it down. What I could do, yeah, this is a good way of setting the current limit. I'll turn the current down and then see if I can turn it. It's still pretty tight. Turn it down more. It's down to 1.2 amp in its hold now. I can move it. And I'll turn it down a little bit more. Yeah, now I can move it a bit more easily. But the thing is that these couplings are just a force fit onto the stepper shaft. So as the motor gets hot, it could actually be softening the plastic in there as well. Yeah, it's quite noticeably warm now, like it's cozy warm. It's like a little pocket hand warmer. So I'm going to turn the current back up to about 2 amps. And then I think what we would do is have it in cycle mode, not constant mode. But at least that's kind of proved the point. So I'm going to set M1 to in cycle mode. And it's just powered down. Nice. So now I can do G0X. I'm going to go to 150, which is the maximum travel according to the settings. And I'm going to hit enter, and we should see this spin. Yeah, it did the same thing again. It started to spin and then it stopped. So I'm going to increase the current a little bit. All right, and then I'm going to try it again. It could be that I need to do something with those motor couplings to, yeah. I'm hitting current limit on the lab power supply. I set 8, and yeah, okay, I've just increased the power supply. Also, what I should probably do is up the voltage, because I'm only running 12 volts on these. I could be running 24 volts, no problem, which would then allow me to decrease the current, I think. So, let's, now that I've increased the current on the lab power supply, it's hitting 4 amps. Yeah, interesting. Okay. Now that the motor has heated up, it is pulling more current, and it does not seem to be. I'm seeing how tight this coupling is. I'm trying to pull it up. I can't pull it up off the shaft, but it is possible that it is no longer binding to it. And I can't see the shaft on the back to tell if the motor is spinning when this is stationary. Let's see if I can reveal that. Because what I can't tell is whether the motor is spinning and its shaft is spinning, but the coupling is decoupled from it. I'm going to take this out to leave us with just the coupling, and then I'll put a dot or something on the back of the shaft. Yeah, a little mark on one side of it. I don't know how clear that's going to be on camera, but I think hopefully you'll be able to see it. And then we should be able to tell if the motor is spinning and the coupling is not. There's no friction around the outside, so I don't see why that would be the case. I'm pretty confident the motor is not spinning, but I want to check that. All right, so what we should see is the motor start to spin and then vibrate a bit and then start spinning as it's getting to the end of its cycle. Spinning, yep, see, it stopped. The motor itself is not turning, and then it moves a bit right at the end. Okay, so we are not getting the motor spinning properly. The current setting is pretty high. That's maximum on the current setting on that. What else could be influencing this? Oh, Vic says, FYI, I'm running off 12 volts. Yeah, does it need to be more efficient? No. Wagon Load says, if you have access to the back end of the shaft, you can glue a magnetic rotary encoder on the shaft. Yes, absolutely you can. I could turn these into closed loop servos, but it shouldn't be necessary for this project. You know, doing some closed loop servo stuff would be really interesting in the future, but it's right now it's just an unnecessary complication compared to just getting this working. So, all right, to recap, my lab power supply is set to 12 volts with an 8 amp current limit applied. The current limit on the Tiny G is set to maximum. The stepper is pulling about 4 amps when it is moving. And I'm going to, what settings could I try messing with just to see what's going on here? Okay, one other thing I'm going to do. Vic got me to measure the resistance. Oops, I'm going to turn that off. The resistance on coil A. I'm going to measure resistance across coil B.
Mine runs at under 4 amps total.
Yeah, I shouldn't need to be driving this much current into it just to make a motor spin. This is not normal. But we'll see if we can figure it out. Let's see what resistance there is. 4.7 ohms across coil B. Okay, that seems fine. So yeah, stepper motors are typically in the 4-ish ohm range, give or take. So the coil resistance seems okay. What else shall we try? I'm just going to try increasing the voltage. It really shouldn't be necessary. This should not be taking 4 amps to turn, and even then not doing the job properly. So, VSET 24, go, and let's tell it to move again. I'm going to do, oh, disconnected, lost. Power on, booting. Serial port is back. Okay, I'm going to go do a move on this. Yeah, it started, stopped, and then it's going to start again. I have a feeling it's just trying to move too quickly for the stepper to keep up. But that doesn't seem right, given that it is, so motor 1 is set to 1.25 millimeters per revolution. That's something we'll have to change later. Polarity is normal, so that sets the direction. And axis X settings. Velocity maximum 800 millimeters a minute. That is low. That should not be a problem. Let's try. Okay, just for the. Oh no, it doesn't matter. I was just going to change the travel maximum for the soft limit, but that's all right. It doesn't matter for these tests. Feed rate, velocity. As a test, I'm going to bring the maximum velocity way down. So let's do X velocity maximum equals 200 millimeters a minute. And then we are going to do, we're going to send X-axis to 0, back to here. And let's see if this maintains its speed.
What are your steps per millimeter?
There we go. Yeah, so it's maintaining, it's continuing to move the whole time. And it should get there eventually. Yeah, there we go. It got to its destination. I think it is just trying to spin the stepper too fast. That is my suspicion. I'm going to spin that back to 50, and this time I'm going to pay attention to the current. So in motion it's pulling 3.2 amps, which will be partly because, all right, I'm going to turn the current down while it's in motion and see if that fixes it. So current down, I'm going to set it back to the midway point again. Because we're now running really slowly, This may well be enough. Yeah, it's now running 2.3 amps. I'll keep turning it down. Yeah, I could stop it then by, I was making it skip steps then by just grabbing it with my hands. So I'll turn the current back up a little bit. Now can I stop it? Oh, I can, but I've got to try harder. So I think that setting is probably okay. And that is like pulling in the order of 2 amps while in motion. Okay, if I do it on the y-axis, we will probably have a failure because the speed is set to an incorrect level. Okay, where are we? Where are we? Paul, update from here, it's alive, yay! Nice, good one, Paul. Try reducing the top speed to Simon, yes, cool. Vic asked, what are your steps per millimeter? Let's find out. Is it in there? No, it's in the axis driver, so it'll be in X there, and X-axis mode. I'm sorry, my brain just totally misfired. I got distracted by a noise outside. Lost track of what I'm doing. Velocity, steps per millimeter. I saw it in here a little while ago. No, was it steps per millimeter? It was millimeters per revolution that I saw. Maybe I'll make it run faster if you reduce the acceleration value. Yes, that's true. Main limit is the vibration that's caused by high speeds. Oh, someone at the door. Hang on, I've got to go and unlock it. Hang on.
Oh,
hello.
Hi, John. Thanks. I was going to say hello. Thanks.
Yes, so Andy has just arrived. Yeah, so steps per millimeter. I've got 0.9 degree step angle. I've got 1.25 millimeters travel per revolution is the step, is the distance. I don't have steps per millimeter directly because I've got one level of abstraction but between that. So I've got 400 steps per revolution and I've got 1.25 millimeters per revolution. So that means that if we divide 1.25 by 400, that will give us millimeters per step. Or the other way around, if we divide 1.25 by 400, that'll give us, so 1.25 divided by, no, 400 divided by 1.25 gives us 320 steps per millimeter. Okay, I got there in the end. Simon says, time for coffee. Yes. Do stepper motors have a frequency limit on steps? Yes, they will. Yeah, you can only run them up to a certain speed. Let's see. Sorry, I am totally discombobulated now. I've got to think about what I'm doing. Get myself concentrating. What am I trying to do? I need to figure, I don't know. No, I think we've got enough information now that we can move the steppers, but I may have to change the homing direction on the Z-axis based on what Vic was just saying. Tinker says if you try to spin them too
If you
fast.
try to spin them too fast, do you get a trouble ticket?
Maybe. Let's try finding where that limit is. I took it from 800 millimeters a minute to 200 millimeters a minute. Let's do a bit of a binary chop on it. So I'm going to do x velocity maximum equals, well, we know 200 is good, 800 is not. So let's go to 500 and split the difference. And then we'll try to move it. So let's see if this now works. Is it going to spin? Okay, so it seems all right at 500 millimeters a minute. I'm just going to change it to 700 millimeters a minute. And that still seems happy. What'll be annoying now is if I go back to 800 millimeters a minute and it still works. So I'm going to go to 800 millimeters a minute, set it to 0. Oh, what happened then? Failed to get planar. Ah. I got a weird error coming up in the... Look at this. Weird error. Failed to get planar buffer. Error, FB. So that is like an error within the motion planner in the TinyG firmware. And now, I set it to 0 instead of 800. No wonder I confused it. Let's try it. It's already at 0, so let's go to 50. Try that again. No, it doesn't like that. Not open. I think I've really confused it by trying to set that value. Let's do X is currently set to 800 millimeters a minute. Okay. I've broken its little brain. I'm going to hit reset on the controller. I may have just found, I don't know if you technically call it a bug in the TinyG firmware, but if you set the maximum velocity to 0, it seems to have a panic attack and then not be able to recover from it. Now, the max velocity should never be set to 0, but oh well. So let's see. Now, X is set to 800 millimeters. X velocity maximum is set to 0. All right. $XVM, I'm going to set it to 800. Now, it is set to 800. Okay, so I'm going to do G0X50, switch to overhead
Sometimes
view.
they go into hold mode for safety if things go wrong.
Yeah, 800 is too much. You can see that it has stopped. So I'm going to change the setting to 700, back down to here, which was working a moment ago. So I'm running the motor between position 0 and 50. And then let's try this one. Yeah, at 700 it works. So 800 doesn't like, 700 is okay. I don't like living on the limit, so I'm going to bring it back to 600 millimeters a minute max. And I will do the same on the y-axis and the z-axis, which may make the machine run a little bit slower, but hopefully the axes will be correct. All right, so let's do G0X0, to zero it out. So now I'm going to do G0X50, Y50, Z50. So this should make all the motors spin in the same direction. Let's see what happens. Whoa, look at that. We have motor movement. And then if I set them all back to 0 targets, 0, 0, 0. They'll all spin in the opposite direction.
Lazy steppers.
Lazy steppers? Okay. Okay, you're better off running at a higher voltage. Simon said you'd be better off running at a higher voltage. I run my CNC machines at 48 volts. The tiny G does not like 48 volts. What you can do is run the stepper power supply off a different voltage to the main board. But this will be fine. And as Vic said, he runs his at 12 volts. Oh, I'm going to try running this at 12 volts. I've been running at 24 volts. I'm going to repeat this at 12 volts. So I've just changed the stepper supply to 12 volts and go to overhead and run. Ooh, look at that. 2 of those steppers do not want to run at 12 volts with that speed setting. So let's drop it down to, so for the Z, I'm going to set it to 500. And for Y, I'm going to set it to 500. And then we'll try this again. Yeah, they run at 500, but not 600. It could be the reason is that this one was warmed up, and so it was capable of running at a slightly higher max velocity. So for safety, I think we need to set velocity max on all axes to 500 if we're running at 12 volts, because that could be the other factor. So now, doing this, we've got all 3 of them running in one direction, and then if we do this, we should get them all running in the opposite direction. I can't really tell the direction from camera because of the frame rate. Okay, I think we have movement. The speed limit of RepRapMicron is usually determined by the amount of vibration caused. Ah, okay, interesting. And Vic said that kind of power isn't really needed. There is
The
an
speed
80...
limit of RepRapMicron is usually determined by the amount of vibration caused.
Yeah, as Vic says, there's an 80 to 1 mechanical advantage because of the little trapezoidal motion platforms. Wagonland says, try testing the max limit over 700 so you know how far inside that limit you're working in. Yeah. The blue screw is preparing itself for ejection. It is slightly off center. That's right. Now, where are we up to? Okay, I think we are kind of okay. Now, it may be that we need to change some of these settings later once the mechanism is in place, because the motors are going to, at the moment the motors are just spinning, they're not loaded. It might be that they don't like going to that speed when they are loaded, and we won't know until it's actually in place. But at least now we're in a position where we know we can drive the motors, and I haven't tested the homing. We'll have to work that out. So there is going to be a little bit of risk involved in the next step, but I think we're about there. I think what we can do is mount the steppers onto the axis drivers, or at least mount one stepper onto an axis driver and see what we can make it do. Yeah, will it hit me in the face or embed in the ceiling? Take your bets. Place your bets. Okay, so what other interesting settings have we got here? X-axis travel resolution in steps per millimeter. Y-axis maximum rate, which is way higher than mine. X-axis acceleration, maximum travel 6,500 millimeters. So the max travel I've got at the moment is 150, I think. Yeah, 150 millimeters X travel maximum. So one of the odd things to keep in mind with this is that these numbers are going to be total lies because of the 80-to-1 mechanical advantage. So we are going to be, the software that's going to be driving
Those
this...
mm are really microns.
Yeah, that's right. The millimeters become microns because we are going to be lying to the software that controls this, because we are orders of magnitude smaller than it is expecting it to be. So we're going to be giving it target positions in millimeters, but actually moving in microns. And let's set the travel maximum on those three axes. So we'll do XTM, so X travel maximum. I'm going to make this the same as VIX settings for now. So 6500 millimeters on X, 6500 millimeters on Y, and 6500 millimeters on the Z axis. Yeah, Vic says, telling the controller to go to 0.001 invariably results in floating point errors. Wagonley's asked, if it doesn't move, is there a way to use motion feedback to auto-tweak speed until it moves? Short answer is no, because we would need closed-loop control for that. We would need some way of detecting whether it's moving, such as a Hall effect-based or a magnetic encoder on the back of the shaft of the motor. At the moment, it's an open-loop system. The motion controller is sending steps to the stepper and just trusting that it's going to be moving. So if the stepper misses steps, that's bad. And we don't have a way of trapping it at the moment, which is the way typically 3D printers work. This is totally normal. So once we've got this tuned, I don't think this is going to be an issue. It should be fine. Maximum rate, max travel, acceleration, yeah, okay. So homing direction invert mask on 23. I think this means that on the Z axis we need to invert it based on what Vic was saying earlier. So if we have a look on the let's see, Z axis settings, it is search, jerk homing, travel, feed, axis mode, latch, etc. No, maybe it's set in the motor settings. Motor 3, it is, no, oh, maybe it is.
Closed loop is much like hiring someone to watch see if your children did what they were told over the phone.
Yeah, have they done it? Have they done it? Okay, maximum travel, jerk homing, no, jerk, switch min. Okay, switch. So it's got Z switch on the max is set to 1 for homing. There is no switch on the min, which I believe is what we want. That should be the setting. So it's going to home towards the max Z position. Okay, now let's check it on the X axis. It is set to homing on the minimum switch, and there is no max switch. So this should be, and the same on the Y axis, I hope. Yeah, so it is homing on the min position on the Y axis. Okay, that's good. That's good. So the default behavior, which is what you would expect, because typically, so a tiny G board is typically used for controlling a CNC machine. And so what you want is to home your X axis to the minimum position, home your Y axis to the minimum position, and you want to home your Z axis up, because, so to the max height, because that way you're clearing everything below it. You don't want to home it down into like your workpiece, the structure of the machine. You want to home it to maximum clearance. So the default behavior of the Tiny G looks good. We've got homing towards minimum on the X and Y axis, and we've got homing towards max on the Z axis. Yeah, very good. And we've got 0 back off 1 millimeter. So it's going to home, activate the switch, and then back off by 1 millimeter. Cool. Okay, so Vic, you were away during that little summary. The end result, just to summarize for Vic's benefit, because it's important that I get this right. What I was just doing was checking the homing switch directions on the X, Y, and Z axis. X and Y axis are homing to the minimum position. You can see there, X switch homing to the minimum position. And the Z axis is homing to the maximum position. So that is fully elevated. So we've got on the Z axis, we've got no switch set for the min position, and we've got homing set to the max position. So I believe that is what we want. Minimum position X and Y, and then max position homing up on the Z. So that all seems good. Vic says, yep, otherwise you tunnel with the probe. Exactly. Okay. I think we have vaguely sane settings now on the Tiny G. So we can drive, we should be able to home, and I could test that. What I could do is I could tell it to home. Actually, I wonder what the homing speed is. The homing speed, search velocity, 500 millimeters a minute, 500 millimeters a minute. I could back off the search velocity. So we've got 400 millimeters a minute on Z for search and 500 millimeters maximum. I'm tempted to decrease the homing speed, particularly, like what I can do is back it off. So ZSV, let's do this. I'm going to set the Z search velocity to a really slow speed, like 200 millimeters a minute. And I'm going to do that on all of the axes. So Z, and then I'm going to do it on X, and I'll do it on Y, which means while it's homing, it is going to move very slowly. And I want to be really paranoid about this, because if the homing switch does not work, it's going to kind of crash into the structure. And I want to be ready with my slow human reactions to be able to kill power, and then
Big surprise is that an axis does not stop immediately when it hits the end stop.
yeah. Yeah, so it means that homing is going to take patience, because it's going to move very slowly towards the homing switch. And then once I'm confident that the switches are working, I can turn this search velocity back up again and make it run more quickly until it gets to the homing switch, and we will be fine with that. But for now, I want it to be super conservative and not break the mechanism. So I'm going to run search velocity super low. And then once it's homed, it'll be able to run up to its full speed. So 200 millimeters a minute while homing, and then 500 millimeters a minute once it's homed and it's moving to specific target locations. Okay. I think we're kind of good with that. So what this means is that I can, yeah, I can put these steppers into the mechanisms and tell them to run, and hopefully not break anything too much. I hope. Maybe. Okay, let's go. Oh, does it use mechanical limit switch or optics? That is the very next thing. It is mechanical, and it is 2 bits of wire that get pushed into each other. I have some wire right here, which I am intending to use. Let's see what this is. This is 0.7 millimeter stainless steel wire. I am intending to use this for the homing contacts. And where are we? I'm going to find the documentation page that I was on. It is pre-built, main project page, blog. Okay. Here. Nice. Oh, this is what, this is because of what Paul is doing at the moment. So Paul in the chat is currently trying to use NEMA 14 steppers instead of NEMA 17s. And this updated version of the Pika has slots for mounting the steppers, so that on the smaller stepper motor where the four mounting holes are closer together, it'll fit into the slots. So I haven't printed this version. I printed the version before this, which had just the holes for the NEMA 17s. Probe fabrication. Oh yeah, probe fabrication. All right, that's cool, but I'm going to skip over that for now. F-path experiment. Yeah, more probe fabrication. That's using the machine itself to make its own probes. What I was actually looking for was just the build guide. I probably got it open. I've got so many tabs here open. Where is the build guide? This? Here we go. Yes, I did have it open. All right, so done that. Got that in there. We've put that in there. That is in. I've drilled out these nuts so that we've got bearings. I've got loom bands that I can hook around here to do the backlash compensation on the axis driver. And so temporarily onto a 50mm screw to use as a punch for this purpose. Yeah, that's that part. Fitting the loom bands for any backlash. 3 or 4 loom bands, okay. Do not use stretching and slip them under the hooks. Use a long M3 screw to hold them in place. And then screwing drive screw and lower nut bar into the drive nut. This right here is the point that we're up to. Oh, okay, no, I can insert the bearing nuts into the nut bars. That is the, and use it as a punch for this purpose. No, I'm going to use parallel jaw pliers. Okay, this. If not, hit them again with a little more enthusiasm. I like the way Vic puts that. Okay, so I need to put the bearing nuts into these locations. Let's do that. So at least we've got a little bit of mechanical assembly that we can have got through on this stream. Move these out of the way. I've got these bearing nuts. I've got these things. These are the parts that need the bearing nuts in them. And I've got fancy parallel jaw pliers, so I can use these to squeeze them in. And then we can assemble one of the steppers to an axis driver. So these should pop into here, I believe. And doing them with these, it should end up pretty nicely parallel. Of course, I can't put a bolt into it and use it to drive it in because there's no thread there anymore. In fact, yeah, M3 just goes straight through. So then, well, it's kind of cool to have the steppers actually moving. It feels like it's a properly alive thing now. Oop. I need to make it a bit tighter. And since we're getting to the last, where are we up to? The last few minutes of the stream, I want nerd brags. Come on, bring them in. Whatever nerd brag you've got, share it with the class, please. There have got to be some. Okay, so we've got the bearing nuts all in place. What else are we doing? Okay, next steps. Back to documentation. Crispian says, I'm full of pikelets, butter and jam. There is a whole pikelet story. There is a story of sad lack of pikelets. I got out a frying pan with the specific intention of making pikelets this morning and leaving them behind for someone to eat. And I ended up just coming here to prepare for the stream instead. Vic says, no brag, I processed some wild clay and made a wee clay pot with it. Oh, nice. Some wild clay. Grant says, my son made me pancakes for breakfast. It's Mother's Day. Yeah. Yes, that was why I was intending to make pancakes, well, pikelets this morning. But the house was very quiet and I decided that I did not want to be banging around and making noise and stuff before I left to come here and do this. So where are we at to? Okay, I put that in. The end result was I was going to make pikelets this morning and at the last minute I decided not to. Also because I got up about half an hour later than I was intending to. And I did not make them. So that I need to put loom bands in there, hook it around there. What colors are we going to use for these axes? We've got blue, green, and yellow. I don't have any particular strong associations with these colors in terms of what color matches what axis. So I'm just going to I'm going to start with blue. So it's the same as what Vic is doing there. Next step. Let's start with blue. This and this and loom bands. Loom bands is the next thing. So loom bands to go onto this part of the mechanism, hooked under there, coming up, and then I'll put a screw through there. So I need some long M3 screws. A couple of 25s will do. I'm going to need 6 of them. All right. So we've got some M3s. This is going to take some tweezers or something to get them in there. This is going to be slightly awkward. All right, loom bands into that little gap in there, hooking underneath. Okay, 1. I'm going to put in, well, Vic said 3 to 4. I'm not sure how many are actually required. It just changes the tension on the mechanism. And also, I don't know if there's any variation in length of loom bands. I suspect they're pretty much the same, fairly consistent. These seem very short, and I don't know if it's normal. So I'm going to go with 4 and err on the side of having too much tension, perhaps, because I can always cut a band to reduce the tension. Now that ding that just happened on my phone, I'm going to have a look at that because there are logistical things going on today that I need to be on top of. even though I'm doing a stream. Because after the stream, I'm heading to my mum's place. So, hang on, I'm just going to check that message in case it is... oh, okay. Not directly relevant. Loom band colors are going to be like bird identification rings. Oh, okay. Is there a standard color code for the XYZ axis? Says Wagon Loads. That is a good question. There probably should be. Okay, I'm going to hook that over there just to stop them from falling out. They don't seem to have much tension on them. Oh, okay. So Vic has, I'm just looking at the picture on Vic's blog. He's pulled it across to there. That seems to put a fair bit of tension on that axis, which is slightly worrying, but I think it's okay. I'm going to trust in the process. I'm going to trust in Vic. Do the same on the other side of the axis. It's going to be pulling it up reasonably strongly. Well, these loom bands seem to vary a bit in thickness as well. Some are slightly thicker than others, so they'll have more tension. Come on, get under there. That's 3. And get another one on. Wonder if it'd be easier to do this from the other side. I think it's okay. Oh, that last one didn't quite get in there. Come on. I'm dropping them. One that I got in has just fallen out. This is a fiddly part of the process. Okay, try it again. And get the screw through and on. Okay, the loom bands are now holding that up. So next step on the instructions is, okay, stretching them, slip them under the hooks. On the other side, screwing the drive screw and lower nut bar into drive nut. Lightly lubricate the drive screw. I don't think I have any oil here. I should have some light machine oil in like a tiny little squeeze bottle. But I was looking for it a little while ago and I couldn't find it. It's normally on the shelf up to my right. It's gone somewhere. So I need to get myself some light oil to lubricate this. So here we go. This, I'm going to have to try to interpret this photo. So we've got the 50mm drive screw there. It goes through this bearing, screws into that, and then we add these nuts on the top. Stacking nuts and washers on the drive screw, okay? So we put 2 M3 nuts, and that goes onto there, and then that goes on top. All right, I think I understand what's going on. Maybe. Wagonline says, I have sewing machine oil. Yeah, that's the sort of thing that I thought I had somewhere. Oh, okay, Vic says, it is easier to do with the limit switch bracket off, and you can lube them later. All right. Yeah, the limit switch bracket is going to screw onto the end here. You see where these two holes are here? I actually have my limit switch brackets kind of loosely screwed on there. Vic says gun oil. Yes, of course. because it's all about making the bangs for Vic. Okay, I'm going to screw that through there. This is my next challenge. I'm going to hide that away. Where was my... Yeah, that is my drive screw. And at the moment I've got this limit bracket thing on there. I'll take that off in a minute, but for now I'm going to leave it on because it strengthens this and makes it more rigid. So I'm going to screw this. No, I don't do it through that. I've got to put it through... Oh, back to the instructions. I've got to put it through that piece. Okay. It goes through that piece from underneath, like that, and then screws onto there. And I believe this is going to screw onto the bottom like that, with screws going down through these holes into this. Although it may be, I don't know, we'll see. I'm just going to screw this on for now. So it's just sort of in the middle-ish position there somewhere, sticking up. It's hard to see because it's a black bolt. It'd be easier to see if it was silver. Okay, so now I've got to put on two nuts and then two washers onto the top of this. So 2 nuts, 2 washers. I've got 2 nuts, 2 washers, and then we're just about, yeah, I'm not going to run over time today. Too much on. So that, I'm going to run that down, I keep dropping it. Okay, 2 nuts are on, 2 washers, and then the top of this I think goes into the bearing on this piece. It goes into the bearing on that piece, but we're about to find out. Okay, so we have the 2 nuts, 2 washers. Next step. Onto the protruding screw. Oh yes, I've just done this. Approximately 10 millimeters down the shaft. Yeah, about that. I've got it approximately 10 millimeters down the shaft. 2 7 or 8 millimeter M3 flat washers and put these on the shaft. Okay, and then the upper nut bar goes onto the access driver. Nut bar. That is so funny. Okay, so that pushes down that way. So it's going to have, yeah, okay. I'm not going to try to overthink it right now. So I need to take off the limit driver, put the upper nut bar onto that, and I need screws that are going to go all the way down through that nut bar, through this, and into the bottom to clamp that all together. 2 M3 by 50 millimeter screws. Yes. Okay. M3 by 50s. I have those. And in fact for this, funny thing is I've got the half thread. I've got the full thread ones that I ordered specially because I need them. I also have the half thread, so they've got a shaft. These will actually be perfect for this purpose, and I can use them up in this situation because I don't need the full thread all the way down, I think. Let's see. Back to here. Now, I need this, which is the nut bar. Nut bar. Oh, I've got to get it to clear the loom bands. Or do I hook the loom bands over first? I think I need to hook the loom bands. How is that going to work? How does that align? Oh yeah, it does. Okay, so I need to hook the loom bands over the nut bar. I feel like I need 17 hands to do this. All right, that goes through here so that the loom bands are hooked up
Put
over
the
the
legs
top.
inside the loop of loom bands.
Put the legs, yeah, inside the loop. Yeah. Oh. Inside the loop, right there. Yeah, and then it can be hooked over afterwards. So I'll pull that apart, drop that onto the top of the 50mm nut.
Pull out if you need 2 more hands.
Thank you.
4 more paws.
Andy and Astra are offering their services as surgical assistants. So I think this, oh yeah, that works out okay. So I've just got to get that clear. Oh no, they're coming off that part of the hook. All right, I'm going to have to redo a couple of these loom bands. Yeah, they're kind of coming apart. All right, I'm showing how inept I am. I need to redo the loom bands on this side and keep them tensioned so they can't fall out while I'm getting everything into place. The other side I've got on. And okay, so that's 3 of the 4. And 4 of the loom bands are now in place. So what I need to do is keep, I'll try to do it with the wide side of the tweezers, like that. That'll keep them tensioned. And then I can drop this into the middle and maneuver these back up over the top. Maybe. It's kind of working. Yes, got it. Okay, all the loom bands are now coming up over the top of the mechanism. This is, I'll twist that into place if I can. Can I pull that down? Okay, twist that into place. And now I should be able to put the 50mm bolts all the way through, and they should go from there through to here. So in through that hole and then into this back brace. Here we go, we're getting there, and now it should go into that. And then another one into the other side before I do it up tight, just so I can get all of the alignment correct. And then, here we go. We almost have ourselves an axis driver. All right, do that up so that it's nice and solid. And now we have an axis driver. And by turning this, is that right? This does not seem right, but I trust it. Okay, by turning that, oh, it's spinning in the nuts. All right, there's something strange going on here that I don't understand, but I'm sure it'll all make sense once, once I've finished following Vic's instructions. All right, so the loom bands are pulling that up. With my fingers, I can pull it down a bit, so that is stretching the loom bands to pull it down. That's the anti-backlash mechanism. And you can see that the bolt comes down through here. What I should do right at this point, if I was sensible, is look in the chat and see if Vic is shouting at me, telling me what I've made a mistake about. So, let's see. What is going on in the chat? David says, stream police. It's after midday. Yep. Thanks, David. All right, now, where are we up to? So we're at this stage, essentially. Do not tighten the screws yet. The end of the drive screw should be in the bearing nut at this point. Oh, looks good, says Vic. Oh, nice. Words of praise from the master. Tighten them up, nut bars so inside the loops. So not tighten the screws yet. Okay, so that nut goes up against the two. Yes, okay. I think I see what's going on here. So what happens is that one of these nuts is going to be a lock, like these two nuts are going to lock against each other, and then the two washers that are in there are forming a thrust washer. So they will be pushing against each other and rotating, and that applies force against this top bar so that it is being pushed up, and it's basically being squeezed between the top bar and this portion here of the axis driver, which applies a force down against the nut that is in the axis driver and a force up against the nut that is in the, well, it's not a nut, it's the, there's the bearing that is in there, the bearing nut, and then up against these. So, okay, I see where that's going now. I see where you're going with this, Vic. Very clever. Lifting the loom bands, positioning the lock nut. Okay, while maintaining some tension on loom bands to prevent them slipping out, lift the bands onto the top areas. Yep. Loosely fasten the nut bars so that some movement of the pillars against the frame trio is possible. Okay, I've done those up tight. I need to back them off a little bit. Pull the head of the drive screw approximately 1 millimeter away from the lower nut bar. Spin the top nut on the drive screw until it contacts the top nut bar. A small screwdriver is useful for this. Yep, okay. Very good. Try fitting the drive screw into the flexible coupling. Yes. Okay. And then that screws in underneath. I think we are just about there. I just need to do some adjustment on these nuts. So while maintaining some tension on the loom bands, lift the bands onto the top. Pull the head of the drive screw approximately 1 millimeter away from the lower nut bar. Spin the top nut on the drive screw until it contacts. Okay, I believe I understand those instructions. So, let's give it a go. So, pull this, hang on, I've got to switch views. So I've got to pull this down until there is about 1 millimeter of gap under here. So pull that down, and then I need to pull those screws up. So I will drive this screw up here with a little screwdriver, as Vic suggested, and that then provides the drive mechanism. In fact, I'm going to screw that through a bit more because I don't think I screwed this in enough into this intermediate nut, into the drive screw. So spin that up a little bit more. And what I can see is that Vic's positioning has this mechanism in the middle. So I definitely need to drive this screw through more so that we're in the center of the range of motion. So that's now about 1 millimeter away. I'm holding this down with my fingers, applying the tension against the backlash mechanism. Spin that up and until it touches. Oops, I took it a bit too far there. Okay, a little bit too far still. No, I think that's about right. Okay, so now it is holding the mechanism in the center point. It can move up and down, and then I will bring the other nut up against it, and these two nuts need to be turned in opposite directions so that they lock against each other and lock it into position on the shaft. And that way, what we can do is when we turn this end of the 50mm bolt, it will turn in the nut in here and it will be able to move it up and down. Yeah. Okay. Seems all right, I think. I hope. It's looking okay so far. And then we add the axis driver. So this is where the position of this coupling is going to be critical, and that is the spacing that we were talking about last week. So the next thing is just to do a test fit of the motor with the coupling into the end of this bolt. Yeah, so do a test fit. Yep, and then it screws in that way. Yeah, and this is what I was just talking about. So using, in this particular case, it's using hemostats as pliers, very, very thin pliers, to grasp the two nuts and rotate them towards each other so they lock tight onto the thread. And in fact, a bit of Loctite could actually be helpful there. But yep, I'm going to wrap this stream up in a minute. I'm not going to go much further with the instructions. So that's, and then this is the limit switch stuff, which will get added on to the end of it. All right, what I'm going to stop with is test fitting the motor onto the end of the nut, like this, right here, onto the head of this bolt. So that is what I'm going to do next. I'm going to take this axis driver. This is all still powered up too. I'm going to turn off the tiny G because I'm not going to run that again today. Take that bolt out, and I want this. Oh, I'm going to remove this so that we can see what's going on. That is part of the limit switch mechanism that is going to be reinstalled. All right, so now this should go onto here with this engaging with the coupling, and it is just a little bit too far away. So what I need to do is decrease the gap here. At the moment I've got a 2mm spacer, and I want to raise it so that that coupling engages with the bottom of this bolt. Now I could bring the bolt further down, and I can also decrease the thickness. So I think what I'm going to do, this is going to be done off stream, I'm going to print another spacer, but at 1mm thickness. This is a 2mm spacer. I'll print a 1mm spacer, which will raise the whole motor and allow it to engage with the end of this bolt a bit better. And then it bolts on through here. And then, apart from the limit sensor, we will have ourselves an axis driver. So yeah, that kind of feels like actual progress today. We've had the motors running, we've got an axis driver just about assembled, and we are getting closer to being able to drive the Pika around the place. So, yeah, cool. Still, I am still not satisfied with the amount of progress, but it is some. So, oh, Vic says I'm making great success. Great success, yes, great success. Okay,
You are making great success.
Thank you, Vic. I'm going to go and eat cake now. Yeah, so I have probably missed a whole lot of stuff in the chat. I'm sorry. Remember, next weekend is barbecue weekend. So if you are in, I'm going to add this into the chat. Whoop. Yeah, I'm going to see if I can type. No. Oh, what? What am I doing with my keyboard? I don't know. Not putting my hands in the right place. And barbecue, here are the details. If you are in Melbourne next weekend, go and check out superhouse.tv/bbq and come along to the barbecue. And just a reminder, it is not on today. So if you are planning today, don't come. I'm not going to be here.
What?
Got to go and see my mum.
What?
Oh.
Ash was so upset.
Oh.
No.
And, oh yeah, Vic says, one day I'll make the Barbie. Yeah, so I will see you next week. I hope you have a fantastic week. And I will talk to you later. Thanks. Bye.